We've sent spacecraft to every planet in our solar system. But here's something most people don't realize. Each one of these worlds could destroy our technology in completely different ways. Mercury would crack our spacecraft apart with temperature swings of over 1,000 degrees. Venus would crush it under pressure equivalent to being 3,000 feet underwater. And Jupiter? Jupiter has radiation so intense, it would fry our electronics before we even get close. Now, we're going to break down the one unique danger that defines each planet. Not just the obvious stuff you already know, but the specific engineering nightmares that make exploration nearly impossible. You'll discover why Venus is actually more hostile than Mercury, even though it's farther from the Sun. Why Mars' dust is more dangerous than its cold, and why the beautiful rings of Saturn are actually a death trap for any spacecraft. But here's the twist that will surprise you. The deadliest planet isn't the one you think. It's not the hottest, not the coldest, and not even the farthest one. The most dangerous planet to explore sits right in the middle of our solar system, and it's been killing our spacecraft for decades in ways scientists never predicted. Just a moment, guys. Only 13% of subscribers know when we publish new videos. Make sure you subscribe and turn on the notification bell, because without it, you'll miss formats and documentaries you won't find anywhere else. Let's start with Mercury. It might be small, but it holds one of the most extreme temperature ranges in the entire solar system. During the day, its surface can reach a scorching 800 degrees Fahrenheit, hot enough to melt lead. But at night, temperatures plummet to minus 290 degrees Fahrenheit. This dramatic swing of over 1,000 degrees Fahrenheit happens because Mercury has almost no atmosphere to retain heat. On Earth, our atmosphere acts like a blanket, keeping temperatures relatively stable. But on Mercury, the moment the sun sets, all that heat radiates directly into space. For a spacecraft or lander, this creates an engineering nightmare. Materials expand when heated and contract when cooled. But on Mercury, this expansion and contraction would be so extreme that most materials would simply crack apart after just a few day-night cycles. The Bepi-Colombo mission, currently on its way to Mercury, had to be designed with special heat shields and radiators to survive these conditions. Its sunward side needs protection from intense solar radiation, while its dark side must be insulated against the frigid cold of space. But the temperature isn't the only problem. Mercury is so close to the Sun that solar radiation is 11 times more intense than on Earth. This means solar panels, electronic components, and even the spacecraft's structure are constantly bombarded with high-energy particles that can cause permanent damage. Any human mission to Mercury would need to land in one of the permanently shadowed craters near the poles, the only places where ice exists and temperatures remain relatively stable. But even there, astronauts would need incredibly sophisticated suits and habitats to survive. If hell had a planet, it would be Venus. With surface temperatures of 900 degrees Fahrenheit, hot enough to melt zinc, and atmospheric pressure 92 times greater than Earth's, Venus is the most hostile planet in our solar system. That pressure is equivalent to being 3,000 feet underwater in Earth's oceans. It's so intense that it has crushed every single lander we've ever sent there within hours, sometimes minutes. The Soviet Venera missions were the only spacecraft to successfully land on Venus and transmit data back. Venera 7 in 1970 lasted just 23 minutes before being destroyed. The most successful was Venera 13, which survived for 127 minutes in 1982, long enough to take color photos and analyze the soil. But the pressure isn't the only problem. The atmosphere of Venus is 96% carbon dioxide, with clouds made of sulfuric acid. Yes, actual acid rain that would corrode any exposed metal or electronics in seconds. The thick atmosphere also creates a runaway greenhouse effect, trapping so much heat that Venus is actually hotter than Mercury, despite being much farther from the Sun. This makes cooling systems useless. There's simply nowhere for the heat to go. Interestingly, about 30 miles above the surface, Venus's atmosphere has Earth-like pressure and temperature. Some scientists have proposed floating cities in Venus's clouds as a possible colonization strategy. But even there, you'd be surrounded by sulfuric acid clouds and still need to deal with the planet's slow rotation, One day on Venus lasts 243 Earth days. For now, Venus remains the least explored terrestrial planet, and any future mission will require revolutionary material science to withstand its brutal environment. Mars might seem like the easiest planet to visit, and in many ways it is. But don't let that fool you. The red planet has its own set of deadly challenges that make long-term human presence extremely difficult. First, there's the dust. Martian dust is everywhere, and it's not like Earth dust. It's extremely fine, about the consistency of talcum powder, and it's electrostatically charged, which means it sticks to everything. During the planet-wide dust storms that occur every few years, this dust can block out the sun for months, as happened to NASA's Opportunity rover in 2018. The storm was so intense that it covered the rover's solar panels, cutting off its power supply and ending its 15-year mission. But dust is just the beginning. Mars has almost no magnetic field, which means the surface is constantly bombarded with cosmic radiation and solar particles. On Earth, our magnetic field deflects most of this radiation, but on Mars, it reaches the surface unimpeded. Astronauts on Mars would receive about 0.67 millisieverts of radiation per day, roughly 40 times more than on Earth. Over the course of a typical 500-day Mars mission, an astronaut would absorb enough radiation to significantly increase their lifetime cancer risk. The thin atmosphere presents another challenge. At less than 1% of Earth's atmospheric pressure, Mars doesn't have enough air to breathe or to provide any meaningful protection from meteor impacts. Even small meteorites that would burn up in Earth's atmosphere can reach the surface of Mars at full speed. Then there's the cold. Average temperatures on Mars are around minus 80 degrees Fahrenheit, though they can drop to minus 195 degrees Fahrenheit at the poles. Any habitat would need constant heating, and going outside would require heavily insulated spacesuits. Finally, Mars has toxic soil. The regolith contains perchlorates, chemicals that are harmful to humans and would need to be removed before the soil could be used for growing food. It's why Matt Damon's potato farm in The Martian would have required extensive soil processing in reality. Despite all these challenges, Mars remains our best candidate for a permanent human presence beyond Earth. But make no mistake, living on Mars would require constant vigilance and life support systems that cannot fail, even for a moment. Now, you might be thinking the radiation of Mars is the worst we'll encounter. But remember that deadly planet I mentioned at the beginning? The one that sits in the middle of our solar system and has been destroying our spacecraft for decades? It's time to reveal the truth, and trust me, what you're about to learn will change how you think about the king of planets forever. Jupiter is a monster. As the largest planet in our solar system, it has a gravitational pull so strong that it shapes the orbits of countless asteroids and comets. But gravity isn't what makes Jupiter so dangerous. It's the radiation. Jupiter has the most powerful magnetic field of any planet in the solar system, 200,000 times stronger than Earth's. This magnetic field traps charged particles from the solar wind, creating radiation belts that make the Van Allen belts around Earth look like a gentle breeze. The radiation around Jupiter is so intense that it would deliver a lethal dose to an unshielded human in less than a day. Even heavily shielded spacecraft can only survive near Jupiter for a limited time before their electronics start failing. NASA's Juno spacecraft, currently orbiting Jupiter, was specifically designed with radiation-hardened electronics and a titanium vault to protect its most critical systems. Even so, its mission had to be carefully planned to minimize time spent in the most intense radiation zones. Europa, one of Jupiter's moons and a prime target for finding extraterrestrial life, sits high in the middle of these radiation belts. It receives about 5,400 millisieverts of radiation per day, enough to give a human a lethal dose in just a few hours. Any mission to Europa would need to work quickly and retreat to a safer orbit frequently. But let's say we wanted to actually enter Jupiter's atmosphere. That would be even more impossible. Jupiter doesn't have a solid surface. It's a gas giant made mostly of hydrogen and helium. As you descend, the atmosphere gets denser and denser, the pressure increases, and eventually, the hydrogen becomes so compressed that it turns into a liquid, and then into metallic hydrogen. At the core, pressures reach millions of times Earth's atmospheric pressure, and temperatures exceed 43,000 degrees Fahrenheit, hotter than the surface of the Sun. No material we know of could withstand these conditions. Jupiter also has the strongest winds in the solar system, with speeds reaching 400 miles per hour. The Great Red Spot, a storm larger than Earth has been raging for at least 350 years, demonstrates the planet's violent atmospheric dynamics. For all these reasons, Jupiter will likely never be visited by humans. Our spacecraft will continue to study it from afar, but getting close to the king of planets is simply too dangerous. Saturn is famous for its beautiful rings, but those rings are actually one of the biggest hazards for any spacecraft trying to visit the planet. Saturn's rings are made of billions of particles ranging from tiny grains to house-sized chunks of ice and rock. They extend hundreds of thousands of miles from the planet but are surprisingly thin, in most places only about 30 feet thick. While they might look serene from a distance, these particles are moving at orbital velocities, about 45,000 miles per hour. A collision with even a small particle at that speed would be catastrophic for a spacecraft. The Cassini spacecraft, which studied Saturn for 13 years, had to carefully navigate around the rings during most of its mission. Only at the very end of its life did it perform the grand finale, a series of daring dives between Saturn and its innermost rings. Like Jupiter, Saturn is a gas giant with no solid surface. It has intense radiation belts, though not as powerful as Jupiter's. It also has winds that reach 1,100 miles per hour at the equator, some of the fastest in the solar system. Saturn's atmosphere is mostly hydrogen and helium, with traces of ammonia, methane, and water vapor. As you descend deeper, the pressure increases until hydrogen becomes liquid and eventually metallic, just like on Jupiter. What makes Saturn particularly interesting for exploration, though, are its moons. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane on its surface. It's one of the few places in the solar system where a spacecraft could land and operate for extended periods. Enceladus, another moon, has geysers of water vapor erupting from its south pole, suggesting a subsurface ocean that could potentially harbor life. These moons are far more interesting targets than Saturn itself. But reaching Saturn takes time. Cassini took 7 years to arrive, and any future mission would face similar travel times. The distance, combined with the dangers of the rings and the radiation, makes Saturn a challenging destination for robotic spacecraft and an impossibility for human visitors. Uranus is the forgotten planet. It's been visited only once, by Voyager 2 in 1986, and we know surprisingly little about it. But what we do know suggests that Uranus presents some very unusual challenges. The most obvious oddity is its tilt. Unlike other planets which spin roughly upright, Uranus is tilted 98 degrees, essentially rolling around the Sun on its side. This means that for half of its 84-year orbit, one pole faces the Sun continuously while the other is in complete darkness. This creates extreme seasonal variations. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. The temperature differences this creates drive some of the most complex atmospheric circulation patterns in the solar system. Uranus is classified as an ice giant rather than a gas giant like Jupiter and Saturn. While it's mostly hydrogen and helium, it also has significant amounts of water, methane, and ammonia. These ices exist in a hot, dense fluid state deep in the planet's interior. Surface temperatures on Uranus average minus 370 degrees Fahrenheit, making it one of the coldest planets in the solar system, despite not being the farthest from the Sun. Its methane-rich atmosphere gives it a distinctive blue-green color. The planet's magnetic field is another mystery. Unlike Earth, which is relatively aligned with the planet's rotation axis, Uranus's magnetic field is tilted 59 degrees from its axis and offset from the planet's center. This creates a lopsided magnetosphere that wobbles as the planet rotates. Wind speeds on Uranus reach up to 560 miles per hour, and the atmosphere shows surprisingly little detail. Very few storms or cloud features are visible. This suggests that most of the action happens deep below the visible cloud tops. The biggest challenge for exploring Uranus, though, is simply getting there. At 1.8 billion miles from Earth, even with gravitational assists, a mission would take 12 to 15 years to arrive. And once there, the combination of cold, radiation and distance from the Sun would make operating a spacecraft extremely difficult. NASA is currently planning a Uranus mission for the 2030s or 2040s, but it would be an orbiter and atmospheric probe only, no landers and certainly no humans. But we've saved the most extreme for last. The final planet in our solar system holds a record that seems almost impossible: winds faster than the speed of sound. Here's why Neptune is the ultimate frontier. Neptune holds the record for the fastest winds in the solar system. Storms on Neptune have been clocked at 1,200 miles per hour, faster than the speed of sound on Earth. Like Uranus, Neptune is an ice giant with an atmosphere of hydrogen, helium, and methane. Its deep blue color comes from methane, which absorbs red light. But, unlike Uranus, Neptune is remarkably active, with visible storms and cloud features constantly changing. The most famous feature is the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot. When Voyager 2 observed it in 1989, it was about the size of Earth. But when the Hubble Space Telescope looked at Neptune in 1994, the Great Dark Spot had disappeared, replaced by a new storm in a different location. This shows how dynamic Neptune's atmosphere is, despite being nearly 3 billion miles from the Sun and receiving only 1/900th of the sunlight that Earth gets. Scientists still don't fully understand where Neptune gets the energy to power such violent storms. Average temperatures on Neptune are around minus 370 degrees Fahrenheit, similar to Uranus. But Neptune actually radiates more heat than it receives from the Sun, about 2.6 times more. This internal heat source, combined with the planet's rapid rotation, one day on Neptune is only 16 hours, drives the extreme wind speeds. Neptune's largest moon, Triton, is one of the most interesting objects in the outer solar system. It orbits Neptune backwards, retrograde, suggesting it was captured by Neptune's gravity rather than forming alongside the planet. Triton has active geysers that shoot nitrogen gas and dust several miles into space. But visiting Neptune presents the same challenges as visiting Uranus, amplified by the greater distance. At nearly 3 billion miles from Earth, even a high-speed mission would take 12 to 15 years to arrive. And at that distance, solar panels are useless. Any spacecraft would need nuclear power. Communication delays are also extreme. A signal from Neptune takes over 4 hours to reach Earth, making real-time control impossible. Any mission would need to be highly autonomous. For human exploration, Neptune is simply too far, too cold, and too hostile. It will remain a target for robotic exploration only, at least for the foreseeable future. So let's take a step back and visualize what we've just discovered together. Picture Mercury, a world where your spacecraft would crack apart from temperature swings of over 1,000 degrees. A planet so close to the Sun that standing on its surface would expose you to radiation 11 times more intense than on Earth. Then Venus, a world so brutal it crushes every lander within hours. Imagine being 3,000 feet underwater, surrounded by clouds of sulfuric acid, in temperatures hot enough to melt lead. That's Venus. Mars, the easy planet that's still trying to kill you. Dust storms that can last for months, radiation levels 40 times higher than Earth, and toxic soil that would poison any attempt at farming. And then Jupiter, the monster we revealed, a planet whose radiation would kill an unshielded human in less than a day. Magnetic fields 20,000 times stronger than Earth's, trapping deadly particles in a zone that makes the Van Allen belts look harmless. Saturn's rings, beautiful from afar, but moving at 45,000 miles per hour. A single grain of ice at that speed would tear through a spacecraft like a bullet. Uranus, rolling on its side with seasons lasting 42 years. A world so far away that even radio signals take hours to reach Earth. And Neptune, the ultimate frontier, winds at 1,200 miles per hour, faster than the speed of sound. A planet so dynamic it creates storms the size of Earth that appear and disappear within years. 8 planets, 8 unique ways to die, 8 engineering nightmares that push the absolute limits of human technology. Now you understand why every mission we send beyond Earth is a triumph of human ingenuity, and why despite all these dangers we keep pushing forward. But here's the thing, we've been talking about visiting planets within our own solar system. What happens when we try to go beyond? Because here's the next roadblock you're going to hit: leaving the solar system entirely. The distance we've been talking about, they're nothing compared to interstellar space. The challenges we've covered, they're child's play compared to what it would take to reach another star. I've done a video that breaks down exactly why leaving our solar system might be impossible with current technology, and what revolutionary breakthroughs we need to make it happen. Click the link on the screen now to discover the brutal reality of interstellar travel. Trust me, if you thought Jupiter's radiation was scary, wait until you see what's waiting for us in the void between stars. Thanks for watching, and stay insanely curious.